So is the screen visible to you?
Yes.
Okay. So in the previous class, we have completed ideal gas equation, right? Do you have any doubts in that ideal gas equation?
No.
Wait a minute. Oh. Is this blackboard okay with you?
Yes.
Okay, thank you. So is there any doubt in gas law like Boyle's law, Charles' law, and Gay-Lussac's law, Avogadro?
No, it's clear.
Okay, then let's start with a question. It will be solving with the help of gas law as well as ideal gas equation. So here is your question. So it's a graph between volume versus temperature, and it is given like this is P1, P2, P3. Now which of the following is correct? Basically, it is a relationship between P1, P2, P3. We need to find.
Okay.
If you are unable to do anything about this, let me know so that I will start explaining. Should I?
Okay. I'll try first.
Okay, try it.
P3 is greater than P2 is greater than P1.
P3 is greater than P2 is greater than P1. It's the wrong answers. Just see how I'm gonna solve it. First of all, whenever this type of question will come, just make clear that put one of these, either volume or temperature as constant. Just see, I'm going to take volume as constant. So I'm going to write a straight line. I'm going to make a straight line like this. What I just did is volume constant. Volume is constant. Now you know that PV equals to nRT. This is ideal gas equation. Okay. As we know that this is a relation between volume and temperature, and in relation between volume and temperature, that is Charles' law, in which what he says is volume directly proportional to temperature at constant number of moles and pressure, right? Is this clear? Volume directly proportional to temperature at constant number of moles and pressure.
Yes.
Now see, what I'm going to do is you can see that volume is constant. Volume is constant. This is constant. Number of moles is constant. And pressure is also constant. Okay, no, the pressure, you are not going to take it as pressure is constant because we need to find out. So here you can see, and R is what? R is ideal gas constant, so it is constant. Now here is what? Pressure is directly proportional to temperature, right? Akifah?
Can you explain again? I got disconnected.
Okay, no problem. This is basically ideal gas equation. PV is equal to nRT. PV equals to nRT. And what I just did is make sure that volume is constant. So this is constant, number of mole is constant, and R is also constant. And you can see here that pressure is directly proportional to temperature, right?
Yes.
From this equation. Now, as we know that this is the graph between volume versus temperature, and temperature is given. So make sure that this is T1, this is T2, or this is T3. So you can see corresponding to T3, since T3 is greater, so P1 will be greater because it is P1 is corresponding to T3. So P1 is greater, T2 is lesser than T3. That's why P1 is greater than P2 is greater than P3.
Okay.
Is that clear? Okay, write
Yes.
it. Can I change the slide?
Yes, done.
Okay, very good. Moving to the next question, the similar question. This is a relation between the graph between P and T. Now this is V3, this is V2, and this is V1. Now you have to find a relation between A option is V1 is equal to V2 is equal to V3. Option B is V1 greater than V2 greater than V3. C is V1 less than V2 less than V3. And none of this. Just find out in the same way that I did.
Okay. Option C.
Option C. Very good. So the very good. Option C is the right answer. Okay, moving to the next topic, which is Dalton's law of partial pressure. Do you know how to find mole fraction?
Given number of moles by
Total number of
Okay.
moles.
Okay.
Total number of moles. Okay, I will tell you how to calculate number of mole fraction. Basically, first we are going to see what is Dalton's law of partial pressure. So Dalton's law of partial pressure says that in a container, if there are non-reacting gases, the gases must be non-reacting. That means if there are some gases A, B, C, or you can see A, B, C, D, any number of gases, the first condition is that they should not react with each other. That means non-reacting gases present in a container. Every gas, every type of gas will apply some pressure on the walls. Either it is A, B, C. And that pressure of each type of gas is called partial pressure. Are you getting my point? This is gas A. It will exert a pressure PA, that is partial pressure of A. This is B. It will exert a pressure that will be called partial pressure of B. This is gas C. This will exert a pressure that will be called partial pressure of C. And according to Dalton's law of partial pressure, when non-reacting gas is present in a container, the total pressure of container will be equal to all the partial pressure of non-reacting gases. Sum of all the partial pressure of non-reacting gases. Is this clear?
Yes.
The gases must be non-reacting. So I'm going to define it. The first point you are going to write: the pressure exerted by individuals in closed container. Individual, the individual pressure is called partial pressure. Individual enclosed container is called partial pressure. Is called partial pressure. So according to Dalton's law, basically total pressure is equal to all the partial pressure, sum of all the partial pressure. Only there is one condition, that this gases should be non-reacting. This gases should be non-reacting. Okay. So then I'm going to write the pressure exerted by mixture of non-reacting gas is equal to sum of partial pressure of each gas at same temperature. There is two conditions: the temperature should be constant, and the other condition, the gases should not react with each other. So this defines Dalton's law. According to Dalton's law, the pressure exerted by mixture of non-reacting gases is equal to sum of partial pressure of each gas at constant temperature. Okay, just write it. If you're done with this, let me know.
Okay. Done.
Done. Write a note. Following gases are reacting. These are list of reacting gases at room temperature. At room temperature, which do not or which don't follow Dalton's law of partial pressure. Dalton's law of partial pressure. So I'm going to make a list of gases, reacting gases that doesn't follow Dalton's law of partial pressure because they do react with each other. So here it is NH3 plus HCl. You can see B is NH3 plus HBr. C is NH3 plus HI. You can also write D is NH3 plus HF. And E is like H2 plus F2. F is H2 plus Cl2. In the same way, G is H2 plus Br2. And H is H2 plus I2. You can also write N2 plus O2. You can also write N2 plus H2. H2 plus O2. And also write H2 plus O2. And you can also write CO2 plus O2. We can also write CO plus Cl2. SO2 plus Cl2. And we can also write N2 plus H2. These are all the gases that that react with each other, so they don't follow Dalton's law of partial pressure. Metal plus X2. X2 basically X is metal should be in vapor. So whenever metal in vapor form comes closer to X, that represents halogens, if you remember. And halogens basically what it is: fluorine, chlorine, bromine, and iodine. So it reacts with each other.
Done.
Done. Very good. So I'm going to derive a formula for Dalton's law of partial pressure. There is a container in which A or B gases is present, or you can say A, B, or C is present, in which number of moles of A is Na, number of moles of B is Nb, and number of moles of C is Nc. N is number of moles. A, B, and C represents that is number of moles of A, B, and C respectively. Is that is that clear? Now,
Yes.
from ideal gas, very good. From ideal gas equation, we know that PV equals to nRT. nRT.
Yes.
I'm going to apply this formula for each and every gases, like pressure of A, the pressure applied by A, the pressure applied on the walls of the container by A, and volume will be same for every gas, because we consider any number of gases present in this container, like 2, 3, 4, 5. All the volumes of gases will be same. So I'm going to write apply for APAV is equal to number of moles of A. R will be constant, and I already said that in the law that temperature is constant. So this is basically for A. And now going for B, so it will be PVV is equal to NBRT. Can I write this?
Yes.
Now this will be PCV will be equal to NBRT, gas 3, for gas 3. And I'm going to apply
NCRT.
Oh, sorry, it will be NCRT. Wait a minute, please.
Okay.
NCRT. Okay. Now come to the point. I'm going to apply here total pressure. PT will be equal to PT into V will be equal to total number of gas into R into T. Can I write this?
Yes.
Now coming to the main point. So this is PTV is equal to NTRT. Now I'm going to divide equation 1 by 4. Equation 1 by 4. So equation 1 is PAV upon equation 4 on the left hand side will be PTV. On the left hand side it will be PTV is equal to on the right hand side of equation 1 you will see NART upon this is NTRT. Okay.
What is T?
T is temperature. Basically, T is temperature. Temperature is constant for Dalton's law of partial pressure.
Okay.
Okay. So now you will see temperature and temperature will be cancelled. R and R will be cancelled. V and V will be cancelled. Okay. Now you will see that PA upon PT. PA represents partial pressure of A. Partial pressure of A. And PB represents partial pressure of B, and PC represent partial pressure of B. Now you will see that PA upon PT will be equal to NA upon NT. And what is NT? NT is total number of moles of the container in the container. Now you will see that NT is basically number of moles of A plus number of moles of B plus number of moles of C. So I'm going to write PA upon PT will be equal to number of moles of A upon number of moles of B, number of moles of A plus number of moles of B plus number of moles of C. And you will know that you know that this is basically mole fraction. This is basically mole fraction of A. You know how to find mole fraction. Basically, you whenever there is a container, here it is a container and there is 1 and 2, and the number of moles of 1 is N1 and number of moles of 2 is N2. So when we find out mole fraction of 1, the representation of mole fraction basically zeta 1, we can say that x1, it is like x1, we call it zeta. So you will see zeta 1, that means mole fraction is equal to mole fraction of A will be mole fraction of 1 will be in numerator, and total number of moles including 1 is the mole fraction of 1. So from this formula you can see number of moles of A is in numerator and total number of moles including A in the denominator, that is mole fraction of A. Is that clear?
Yes.
So I'm going to represent it by zeta A, that is zeta. And here it will be PA upon PT. And in the same way, you will see that PA is equal to zeta A upon PT. PA, what is PA? PA is partial pressure of A.
A.
Partial pressure of A, and PT is basically total pressure. Total pressure. And zeta A will be mole fraction of A. Mole fraction of A. In the same way, we can find PB, PC, PB and PC. So can I write directly as PB will be mole fraction of B into total pressure?
Yes.
And I can also write PC will be mole fraction of C into total pressure, right?
Yes.
So this is the formula for Dalton's law of partial pressure. Dalton's law of partial pressure. I'm going to show you again. Please write it and let me know. So this was it.
Done.
Done. Very good.
Done.
Very good. So basically we need to find, we just know that how to find parcel pressure with the help of this formula.
Yes.
If you're done with this, let me know. I'm going to give a question on this topic.
Done.
Okay. So basically here is your question on neon dioxygen mixture contains 80 gram, or you can say wait a minute, 64 gram dioxygen and 180 gram neon. If pressure of mixture of gases pressure of mixture of gases in the cylinder is 25 bar, what is the partial pressure of dioxygen and neon in the mixture? We need to find partial pressure of dioxygen as well as neon. If you are unable to think anything about this, let me know. I'll explain you. Should I start?
Okay.
Okay, just see here. There are two gases, that is neon. This is noble gas, and dioxygen, that means they are not reacting, non-reacting gases. Mixture contains 64 gram of dioxygen. Given mass of oxygen is dioxygen, that means it is talking about O2. Now you will see that another gas, that is neon, 180 gram. If the pressure of mixture of gases, that means total pressure is given as 25 bar. This is PT, total pressure. What is the partial pressure of dioxygen and what is the partial pressure of neon? Now you will see that we have a formula. Partial pressure of dioxygen will be equal to mole fraction of dioxygen into total pressure, right?
Yes.
Akifah? Very good.
Yes.
Mole fraction of dioxygen into total pressure. Again, it is talking about mole fraction, partial pressure of neon. That means partial pressure of Ne, that will be equal to mole fraction of neon into total pressure. In the question, it is given that total pressure is given, but we need to find mole fraction of O2 as well as mole fraction of Ne, neon. So mole fraction has a formula, that is whatever has the mole fraction, whatever mole fraction of O2 will be equal to number of moles of O2 upon number of moles of O2 plus another thing is Another gas is present, neon. So it will be plus number of moles of Na, right?
Yes.
So we are going to find, we need number of moles and only mass is given. So already we know that number of moles, how to find number of moles. Number of moles of O2 will be given mass upon molar mass. Number of given mass is 64 gram and molar mass of O2 is 32. That means it is 2 moles. Again, number of moles of neon is given mass upon molar mass. Given mass is 180 gram and molar mass is 20. So it will be 9 moles, right?
Yes.
So I'm going to just put the value 2 moles and 9 moles in this question, in this solution. This is 2 upon 2 plus 9. That will be equal to 2 upon 11, right?
Yes.
That will be equal to 2 upon 11. So now we have everything, mole fraction of O2 as well as total pressure, right? So just I'm going to put the value again. Parcel pressure of O2 is equal to mole fraction of O2 into total pressure. That is, mole fraction is 2 by 11 into total pressure, that is 25. And you will solve it, you will get it in bar. Again, for mole fraction of parcel pressure of any, we need to find mole fraction of any. Mole fraction of any will be, that is neon, number of moles, that is n, 9, and 9 plus 2, that will be equal to 9 by 11. Again, number of moles, parcel pressure of neon will be 9 by 11 into 25. This will be in bar. Is that clear?
Yes.
Thank you. Just write it. If you are done with this, let me know. I'll slide down.
Almost.
Done, Akifah?
Yes, done.
Okay, just write it. Slide change करूं?
जी.
Okay. I'm going to I just make a list about which are reacting gases. Now just write a point. It is applicable, that means Dalton's law of partial pressure is applicable for noble gases. Do you know what is noble gases?
Yes.
Noble gas plus gas. Whenever there will be noble gas and other gases, they won't react with each other. Noble gas plus noble gas. See, alkane plus alkane. These do not react with each other. Just write it. Done?
Yes. That's
Okay.
alkane plus alkane, right?
What you just said, Akifah, is it done?
It's alkane plus alkane or
Yes,
alkane
it's
plus.
alkane. Alkane plus
Okay.
alkane. Okay.
Okay, done.
Okay, now we have another topic, which is Graham's law of diffusion. Graham's law of diffusion or effusion. Graham's law of diffusion or effusion. Now you will see that I'm going to write a statement about it. Write with me, then I will explain. The movement of gas in available space is called diffusion. The movement of gas in available space is called diffusion. Another statement about this. It is the same statement as the earlier. The movement of gas from a small orifice, that means hole, a small orifice, that means hole, is called effusion. Is called effusion. So you can see if there is gases and they are moving from each other, this they are moving in the available space, that is called diffusion. And there is a container and there you make a hole, it will move out, that is called effusion. Is this clear?
Yes. Done.
Okay. So what is basically Graham's law of diffusion? So just write, according to Graham's law of diffusion, according to Graham's law of diffusion, the rate of diffusion or effusion, the rate of diffusion or effusion is inversely proportional to is inversely proportional to the square root of their molar mass. The square root of their molar mass. So according to Graham's law of diffusion, rate is inversely proportional to the square root of molar mass. So if we have two gases, uh, if we have two gases, just suppose there is two rate, that is R1 is inversely proportional to under root of M1 and R2 is inversely proportional to M2. So if we are going to take ratios of this R1 by R2, it will be like under root of 1 upon M1 and under root of 1 upon M2, and it will be R1 by R2 will be, this will be in numerator and this will be in denominator, so that it will be inverse to each other. You can see R1 in numerator and M1 in denominator. R1, R2 in denominator, it will be in numerator. So should I slide up, or you are done with the previous one?
Done. Can you scroll down?
Yes.
Can
Yes,
you
yes,
scroll
yes,
down?
yes, yes.
Done.
Very good. Now you will see different types of form of Graham's law. As you know that this is the first form of Graham's law, that is R1 upon R2 will be equal to M2 upon M1. Okay. Another form in terms of pressure. You know, if we will increase the pressure, diffusion will be faster or slower? Tell me.
Faster.
Faster, that means rate of diffusion will be directly proportional to pressure, right?
Yes.
So here we are going to have another form that will be equal to R1 R2, and here it will be, since it is faster, that means directly proportional. So I'm going to write P1 upon P2 and M2 upon M1. This is another form of Graham's law of diffusion. This one is first, then second, then we will have third. Done.
Yes.
Okay. Another form of another form of uh, Graham's law of diffusion, rate of diffusion of gas in terms of volume. In terms of volume, then we will have a formula, rate equals to volume of gas. Wait a minute, please. It's disturbing. Rate is equal to volume of gas upon time taken. Rate is equal to volume of gas upon time taken. So from this formula we can get R1 upon R2, that will be equal to R1 for V1 upon T1 upon V2 upon T2. Then we will get another form, R1 by R2 will be equal to V1 upon T1 into T2 will be in numerator and V2 will be in denominator. Let me know if you are done. Done.
No.
Okay, okay. Write it and let me know. Now we are going to have a question.
Done.
Done. Very good. So here is a question. Write the order of rate of diffusion. Write the order of rate of diffusion of following. A is O2, B is CH4, C is N2, and D is helium. Please write it.
Done.
Done. Which your answer?
No, no, just a question.
Okay, okay. Please answer me, or I should start explaining.
Yes, if you can.
Okay. What is the mass of O2? That is 32. What is the mass of CH4? That is 16. And what is the mass of this? 28. And what is the mass of He? That is 4. Now we already know that rate is inversely proportional to under root of m, molar mass. So if molar mass increases, that means rate of diffusion decreases, right?
Yes.
That may and if molar mass has lower value, that means rate of diffusion is higher value. So lowest value of mass will be D, that is helium, then CH4, then N2, and then O2, right?
Yes.
Okay, so please read all this, and we will have KTG in the next class, that is kinetic theory of gases,
Okay.
and then real gas. Okay.
Okay.
Okay, thank you.
Thank you.
Thank you.